So we'll move on to a new topic in this class. We will talk about finite groups and subgroups. First, to understand what is a finite group, we need some definitions. First definition is the order of a group. So the number of elements of a group. Actually, a group consists of a set and an operation, but with slight abuse of notation, we say that the set itself is a group. So we say G is a group. In actuality, it is G with the operation plus multiplication or whatever it is. That is a group. So the number of elements of a group, by that we mean the number of elements in the set G of a group. Whether it is finite or infinite, it is called the order of the group. And the notation for that is we will use this symbol, uh, two dashed line, two vertical lines around G to denote the order of G. This is similar to the cardinality of set. This is defined as the number of elements of the set. And that's also denoted by the same symbol. But here, instead of calling it cardinality for a group, we call it the order of the group. That is for a group, but there is also a notion of order of an element. And the order of an element small g in a group capital G is the smallest positive integer n such that g power n is the identity. So for any element g, we earlier we saw that in one of the problems, if the group is finite, there is always some number n such that g power n is the. And the smallest of such numbers is called the order of the element. In additive notation, this would be written as ng. So here g power n is nothing but g into g into g n times. Here ng is nothing but g plus g n times. So n times, if you do the operation, with G as the element each time. Or actually, you do the operation n minus 1 times with G as the operand each time. Then you should get the identity. If such a number exists, that is called the order. So if no such n exists, it is possible that there is, for some element, there is no such n. Then we say that the element G has infinite order. So this is defined in such a way that it matches with the notion of order of the group. If the group is of finite order, then all its elements also have finite order. And if there is some element that has infinite order, then the group will have infinite order. So the notation is again similar. The order of an element G is denoted by this notation. So in this case, it is not the absolute value. Don't get confused with absolute value because absolute value also uses the same notation. But for a group, this is the smallest positive number such that G power n is equal to the identity element. For example, consider U15, which is all the numbers greater than or equal to 1 and relatively less than 15 and relatively prime to 15. So 1 is relatively prime to 15, 2, 3 and 15 have a common factor 3, so it's not relatively prime. 4 is relatively prime. 5 and 15 have common factor 5. 6 and 15 have common factor 3, 7 and then 8. 9 and 15 have common factor 3. 10 and 15 have common factor 5. 11, 12 and 15 have common factor 3. Then 13 and 14. So these are the 8 elements of U of 15. And the operation is multiplication modulo 15. Now the order of the group U of 15 is there are 8 elements. So the order of the group is 8. The order of the identity is 1 always because 1 power 1 is simply 1. Similarly, in an additive group, 0, 1 times 0 is simply 0, which is the identity. So 1 is always the order of the identity element. Then 2 power 1 is to find the order of any other element, you simply take the powers of that element until you get the identity, or you show that you can't get the identity. So 2 power 1 is 2, this is mod 15 multiplication. 2 square is 4, 2 cubed is 8, 2 power 4 is 16, which is 1 in modulo 15. So 2 power 4 is the smallest integer such that 2 power that integer is 1. That's why the order of the element 2 is 4. If you take the number 3, then 3 power 1 is 3. 3 square is 9. 3 cube is 27, which is 12 in modulo 15. 3 power 4 is 3 into 12, 36, which is 6. 3 power 5 is 3. Sorry, let me see. I must have made a mistake. No. 3 square is 9. 3 cube is 27, which is 12. I think I wrote 13. Yeah, it is 12, not 13. So 3 power 4 is, oh, maybe I wrote 12 actually. 3 power 4 is 6. And 3 power 5 is 18. Sorry, what am I doing? 3 is not even a member of this group. That's why it is 3 is not a member of U of 15 because 3 and 15 have a common factor. They are not relatively prime. So it will keep going there. You will never get 3 power something. It's 1. No, 3 power 6 was 3, right? Which was equal to 3 power 1. So it will 3 power 7 will be again 9. It will keep repeating. It doesn't have any inverse. 3 doesn't have any inverse. No, you wouldn't get 1. You can't get 1 because 3 doesn't have any inverse in Z15. No, you see 3 power 1 is 3. 3 square is 9. 3 cube is 12. 3 power 4 is 6. Then 3 power 5 is 3. So it will again repeat. 3 power 5 is 3. 3 power 6 is 9. 3 power 7 is 12. 3 power 8 is 6. It will keep repeating. Can't get 1 right. 3 power 9 is again 3. Yeah, so it will keep repeating. Only 3, 9, 12, 6 is what you'll keep getting. Otherwise, if 3 power something was, we already know 3 power 1 is 3, so it's not 1. So suppose 3 power a is equal to 1. Then 3 times 3 power a minus 1 is 1, right? That would mean 3 power a minus 1 is the inverse of 3. But 3 doesn't have an inverse in this, if we considered Z15. First of all, 3 is not a member of U15, so it doesn't make any sense. But instead of U15, if you consider Z15 and multiplication modulo 15, then yeah, it will keep repeating. But that's okay because 3 is not a member of U15. I was only talking about members of U15. So then 4 power 1 is 4. 4 square is 16, which is 1. So order of 4 is 2. 7 power 1 is 7. 7 square is 49, which is 4. 7 cube is 28, which is 13. 7 power 4 is 91, which is 1. The order of 7 is 1. And so on. You can check that the order of 8 is 4. The order of 13 is also 4. The order of 14 is 2. So a trick to find these calculations, to make these calculations easier. For these larger numbers like 14 and 13 is 14 is equal to minus 1 mod 15. So 14 square is minus 1 times minus 1 mod 15 or minus 1 square mod 15. So it is 1 mod 15. That's why 14 has the order 2. Similarly, 13 is minus 2 mod 15. 13 square is 4 mod 15. 13 cube is minus 8 mod 15. 13 power 4 is 16 mod 15, which is 1. So order of 13 is 4. As the number becomes closer to n, instead of dealing with the number itself, you can take n minus that number. Or, sorry, not n minus that number, the inverse of that number. Uh, Wait, what am I saying? Uh, it's not the inverse. Uh, you could shift the number by n. How about say? Anyway, you use modular arithmetic to change the number from a bigger number to a smaller number. Then you can deal with the smaller number easily. Yeah, you subtract uh, n from that number, then that will give you a smaller number. But subtracting n doesn't change the number as far as modular arithmetic is concerned. So a mod n will be the same as a minus n mod n. So instead of dealing with 14, you can deal with 14 minus 15, which is minus 1. And instead of 13, you can deal with 13 minus 15, which is minus 2. Of course, for numbers that are in the middle, for example, 7 and 8, you'll have to do the calculations yourself. And if the group is much bigger, then the middle numbers are also much bigger and they might not have orders which are small. Anyway, in abstract algebra, we'll only consider these examples to understand what is happening. But if it's a very large group with a large n, we won't write down the elements and try to do all this. We'll try to talk in abstract terms. and we'll try to see how many terms have what order instead of asking what is the order of 7, we might say if the order of 7 is what, if something, then what is the order of 7 square or 7 cube? So how are those two related? And we might also deal with um, how many elements are there with a particular order. We might not be interested in what the elements are that have that order, but the number of elements that have a particular order might be enough. The second example, just to make it clear, uh, so instead of multiplicative notation, we'll consider additive notation just to get an idea. Consider Z10, so now it's under addition modulo 10. So the set is 0 to 9. Now, again, like I said, 1 times 0 is 0. So the order of, what is the order of Z10? How many elements does Zn have for any n under addition modulo n? How many elements are in Zn under addition modulo n? Yes, there will be n elements because 0 is also included. 0 to n minus 1. Then what about u of n? How many elements will there be? Yeah, yeah. So here Z10 will have 10 elements, and order of 0 is 1, that is okay. Order of, what is the order of 1? Here it's addition, so it is, yeah. So if you add 1 9 times, you will get, if you add 1 10 times, you'll get 0. So order of 1 is 10. Then 2 ones is just 2. 2 times 2 will be 2 plus 2, 4. So on 5 times 2 will be 2 plus 2 plus 2, which is 10. So that is 0. So the order of 2 is 5. What is the order of 3? So here for integers, the nice thing is that when we mean the notation n times a, in a general group, it is a plus a, etc. So a appears n times in this expression in a general group. But for integers, it also happens that you can do integer multiplication itself. So adding a n times is same as multiplying a by n in integers. So in a general group, that need not be true. There might not be any meaning to multiplying a group element by an integer. So for you, if it's a group of functions uh, with composition, then uh, raising it to a power, there the analogous thing is raising to the power n, right? So it's not actually the same as raising an integer to a power n or raising a number to a power n because they are functions. So here also uh, NA does not mean you are multiplying n and a because n need not be a member of the n is some integer and the group might not contain integers at all. But it just so happens that for integers and even in this case modulo addition and multiplication, n times a is simply the same as multiplying n and a. So now if n is the order of 3 and I say you have to add 3 n times, then that's the same as saying 3n is a multiple of 10. And we know that uh, the multiple of 10, smallest multiple of 10, that is also a multiple of 3 is 30. Yeah. So I guess we can relate it to the LCM, the uh, order of some. Okay, if it's integers, we can do that, but this is modulo 10, so uh, maybe not. So now 3, again, you have to add 10 times to get 30, which will bring it to 0. So yeah, I guess it works in this case also. So to find the order of a number in Z10, find the LCM of that number with 10 and then divide it by that number. So order of A is LCM of A comma 10 divided by A. So LCM of 2 and 10 is 10. 10 divided by 2 is 5. LCM of 3 and 10 is 30. 30 divided by 3 is 10. Yeah. So the order of 3 is 10. Order of 4 is 5. Order of 5 is 4. No, it's 2. Order of 6 is 5. Order of 7 is 10, I guess. Order of 8 is 5. Order of 9 is 10. So all the numbers that are relatively prime to 10 will have the order equal to 10. So Z10 only contains 0 to 9, and these are the orders. So that is how you find the order of an element in general. You simply have to write the powers. Unless you know some property of the elements of the group that can help you solve this problem. Otherwise, you will simply have to write all the powers and see which is the smallest integer at which it becomes equal to the identity. Now, we had made a distinction between finite and infinite orders that would suggest that there are groups where the order is not finite and there are elements of groups that do not have a finite order. And the next example is one such example. This is simply the uh, set of integers under ordinary addition. So here the group has infinite order because it has infinite number of elements. I'll simply write it as order of z is infinite, but this is not correct notation. People don't usually use this notation. I'm just writing it. So don't use it everywhere. Then um, order of zero, order of the identity is always one. So order of zero is one. But for any integer not equal to zero, what will be the order? No, you haven't understood the concept then. See, you have to add A itself, A to itself. You can't add some other element and bring the identity. Yeah, so how many times you have to add A is uh, the least number of times because what happens is uh, here, for example, 5, if you add it twice, you'll get 5 plus 5, 10, which is the equal to 0, the identity. But 5 plus 5 plus 5 plus 5, which is 5 added 4 times, is also 0. Yeah. And 5 added 6 times is also 0. So all those will be 0. That's why we are looking for the smallest integer such that you add the same number again and again. So here also you have to add the integer to itself and then try to get the identity. So then what will be the order? Any integer. You can take a specific example. What is the order of 1? Yes. Normal, integer addition. Yeah. So there is no positive integer n such that n times 1 is 0. Yes. So for any integer, if you keep adding it, you will never get 0. So the order will be infinite. So I'll write it as infinite, but really that symbol shouldn't be used too much. So this is an example of a group where the group has in or elements of infinite order. And once it has elements of infinite order, the group is also of infinite order. And why is that? Why is if an element of a group has infinite order, why should the group be? Infinite. Yeah. But then, what if two of those powers are equal? What if it is repeating like I did for the case of 3? A for any element a square, a cube, etc., a power n, etc. You can keep going. They should all belong to the group. That is true. But then uh, it's only infinite if they are distinct, right? What if some of them are equal? Yeah. But what I'm saying is, if an element has infinite order, then why can't it repeat? Why should it has infinite order means uh, there is no element a n such that a power n is equal to e, right? That's all that it means. From that, how do you infer that these are all distinct? What if there is no element n such that a power n is equal to e, but a square, etc., a power n are not distinct? Can that happen? Is what I'm asking. No, what? For example, we saw here, right? That here, when I took 3, 3 power 1 was 3, 3 square was 9, 3 cube was 12, 3 power 4 was 6. Then we got back 3 power 5 is uh, 3 again. So it was repeating like this. So if they repeat, then that is not an infinite set, right? But how is that related to this condition? If this is true, why can't they repeat? If if such an end does not exist, if there is no end, if there is no end such that a raised power n is equal to e. Suppose there is no integer like that. That means that a element has infinite order, right? But how is that related to saying these are all distinct? Why can't it have this infinite order, but a square, a cube, and then this will again repeat after a power k, then a power k plus 1 is equal to a. Why can't this happen? What's the problem now? No, that's not true, right? Why should k plus 2 be equal to 2? We had a 3 power 1 was equal to 3 power 6, but 6 is not equal to 1. So you can't equate exponents like that. Now from here, how can you show that? So I am saying there is no n such that a power n is equal to e. And then I'm also saying that it repeats like this, that two of the powers are equal. How can you show that those both of those conditions are not possible simultaneously? I'm saying there is no such n. There is no n such that a power n is equal to e, is what I'm assuming. No, but there might be some element b such that that is the inverse of a. Maybe the inverse of a is not a power of a. It is some element b in the group. Suppose a power m was equal to a power n, and without loss of generality, I'll take m to be the bigger number. Then I can multiply by a power minus n on both sides. I'll get a power m minus n is equal to a power 0, which is e, right? Then since m is greater than n, m minus n is a positive number. It is greater than 0. So this m minus 1 will be a number such that a power m minus n is equal to e. So then this is false, right? I showed you an integer, positive integer m such that a power m is equal to e. This is the same argument we used to show that in a finite group, every element has an inverse. Uh, in a finite set, you don't, and if closure is satisfied, you don't have to check for inverses. Closure is enough. So we had seen one problem like that. In a finite group, show that every element has, or in a finite set in which closure is satisfied, show that every element has an inverse. So something like that, some problem like that we had solved, and that had the same logic. So both these things can't simultaneously happen. The order, I can't say that the order is infinite, but some of the powers are identical. That can't happen. If the order is infinite, then every power of A must be distinct. Each of them must be a different element. Only then that is possible. So since each element is different, there are an infinite number of powers of that element. You can raise it to any integer power. They will all be different. So there are an infinite, and by closure, there are an infinite number of elements in the group. So the finiteness or infiniteness of an element doesn't directly say that if an element has infinite order, then each of the powers of that element is distinct. Doesn't directly say that. You have to prove it this way. It is implicitly said by that statement, I guess. So you can easily assume that if there is at least one element of infinite order, the group is also infinite order. And if all the elements have finite order, then the group also has finite order. So once we are done with all that, next that is pretty much it about finite groups for now. We'll come back to it later, maybe in some examples, and when we are dealing with cyclic groups, we'll see if the cyclic group is finite, what will happen. So we'll come back to that later. Now we'll move on to subgroups. I'll define what a subgroup is first. So you have a group G with some operation. Then if a subset of, it's a subset, I'll call it capital H, of a group G is itself a group under the operation of G. We say that H is a subgroup of G. Then we use the notation H less than or equal to G. Different books might use different notation. We will be using this to mean that H is a subgroup of G. Now, by this definition of subgroups, there are two very easy subgroups that you can have for any group. Can you tell me what those are? Yeah, yeah, yes. So those are two subgroups that every group has, and most of the time we'll ignore those. We'll try to ignore those two subgroups, but we'll still give them names. So the first one you said, the subgroup containing only the identity element, is called the trivial subgroup of any group G. And if it is not a trivial subgroup, we'll simply call it a non-trivial subgroup of G. Subgroup that is not E is called a non-trivial subgroup of G. Then the other thing was G is always a subgroup of G. Now, if we want a subgroup that is not the whole group, and we give it a special name, if we want to indicate that H is a subgroup of G but is not equal to G itself. We write H less than G. Such a subgroup is called a, what do you think it is called? This subgroup is similar to the idea of subsets. Yeah, similar to a proper subset. Here we call it a proper subgroup. Okay. Then we'll discuss some subgroup tests. How to test whether some subset you take. So a subset can be mentioned most of the time when you are defining a set or a subset. You will not always mention the elements of the set. Only for common sets like natural numbers, rational numbers, you might write out 1, 2, 3, dot, 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 or minus 3, minus 2, minus 1, dot, dot, dot. And you might write it in that form. But most commonly, you will write set in the set builder notation, that is, by stating a condition. So a subset is also subset might also be defined using a condition to pick the elements of the set. So how do we get the subset H? You might say from G take some elements with a certain property. Only when such a property is given, how do you check if if it is a subgroup or not? For that, we have a few tests. So next we'll deal with those tests. But before that, I will take a 5-minute break. I'll drink some water and go use the washroom and come back. Is that all right? Are you here? Shall we continue? Okay. First test is called the one-step subgroup test. Let G be a group and H be any subset of the group. So any non-empty subset. An empty set can't be a group. So a subgroup is also a group. It's just that it's a subset of a bigger group. And in a group, we always need the identity element. So a group can't be the empty set. And in the test, we assume that the subset you're taking is already a non-empty subset. If it is empty, it can't be a subgroup. So let G be a group and H be a non-empty subset of G. If AB inverse is in the group, is in the subset, not the group. If AB inverse is in H, whenever A and B are in H. So if you pick any two elements of H, A and B, then A times B inverse must be in the set. So by this, what we mean is that you take A and B from H, but that will have and B will have an inverse in G. You take that B inverse, then A times B inverse will definitely be a member of G because G is closed under all these operations. Under the operation and taking inverse is also possible in G. Once you get that AB inverse, that will be an element of G, that is for sure, but is it also an element of H? That you have to check. And if it turns out that AB inverse is in H for all A and B in H, then H is a subgroup of G. So we write AB inverse in the multiplicative notation, but in an additive group, instead of A inverse, AB inverse, it's if A minus B is in H. And A minus B is simply notation for A plus B inverse. In additive notation, B inverse is minus B. That's the notation for inverse of B. So if A minus B is in H, whenever A and B are in H, then H is a subgroup of G. So first thing to note is that operation of H is the same as operation of G. So it is associated. So associative property just says that if you do A times B and then you do A times B times C, that's the same as doing B times C and then doing A times B times C for all elements A, B, C in the group G. But if you take a subset of the elements from G, that property will still hold because it holds for all elements in G. So the associative property is carried over directly to the subset. To show that H is a group under the operation of G, if this condition is satisfied, that is, if AB inverse is in H, we are saying for all A and B in H is a subgroup, which means H is a group under the operation of G. So we have to show that if AB inverse is in H whenever AB and B are in H, then the identity element is in H. We have to show that H is non-empty, and we have to show that H is closed under the operation. How do we show that H has the identity element? No, but my claim is if AB inverse is in H whenever A and B are in H, then it is a subgroup. Then E is in the set. How does AB inverse in H for all AB in H mean E is in H? Yeah. And since in the hypothesis we have assumed H is non-empty, H be any non-empty subset of B. So there is some element in H. Yes, H is non-empty. Uh, there is some A in G such that A is in H. So H contains some element. We're just calling it A. Then by the hypothesis is the assumption that if AB inverse is in H, whenever A and B are in H. Then by the hypothesis, uh, not to get confused, we'll call this X. Set A equal to B equal to X. So if we setting A equal to B equal to X, we'll get X inverse belongs to H. That is E belongs to H. Okay, now we have the identity element in H. How do we show that for any X in G, X inverse is in, sorry, any X in H, X inverse is in H, using the hypothesis? How do we show that the inverse of an element is also in H? No, that is, yeah, that is if H is a group, then that is, you can say out that. But we are trying to show that H is a group, so we are only allowed to use this hypothesis condition. This is the hypothesis. If AB inverse, whenever A and B are in H, AB inverse is in H. Just using that condition, we should show that E is in H, and for any element X, X inverse is also in H. So, like how you showed for E, you said set both A and B to the same element in the hypothesis. So, A is in H and A is in H, and by the hypothesis, A inverse must be in H. That means, but A inverse is equal to E, so E is in H. In the same way, can you show that for A in H or for any X in H, X inverse is also in H? So similar to how you did for the identity, suppose X is an element of H, set A is equal to the identity, since we already show that E is in H. This belongs to H, and B is equal to X. This is in H. Then by hypothesis, AB inverse belongs to H. That is, E times X inverse belongs to H, which implies X inverse belongs to H. Yeah. First, we showed that we can pick any arbitrary element A, and since A is in H, A inverse must be in H. That is, E is in H. Now, since E is in H, for any element X in H, E X inverse must be in H. So X inverse must be in H. Then we have to show closure. If X and Y are in H, XY is in H. How do we show that? Using this condition, using the underlined condition. Yeah. How do we show closure? If X and Y are in H, how do you show that XY is in H? X times Y is in H. Yeah. We just showed that if X is in H, X inverse is in H. So Y is in H. This means Y inverse, I'd call it Y inverse like this, is in H. So X is in H and Y inverse is in H implies X into Y inverse whole inverse is in H. But Y inverse whole inverse is nothing but Y. So XY is in H. So what we are saying is that instead of checking that XY is in H for all X and Y in H, checking that the identity element is in H, and checking that for all X in H, X inverse is in H. Instead of checking these three conditions, you simply check only one condition. That is, if XY are in H, X into Y inverse is in H. If that is true, that condition will take care of all the three conditions. That's what the um, theorem means. For example, let G be an abelian group with identity element called E. I form the set H, a subset of G, is the set of all elements in G such that their square is the identity element. So they either have order 1 or order 2. So set of all elements with order 1 or 2. Now show that H is a subgroup of G. So we will use the one-step subgroup test. What we have to show is if A comma B, first we have to show that H is non-empty. So we have E square is equal to E. So E belongs to H. Thus H is non-empty. Once H is non-empty, we can use the one-step subgroup test. That is, suppose X comma Y are in H. Then this is what we want to show. Then X Y inverse belongs to H. And we can show that in this way. Since X Y belong to H, what is H? It is the set of all elements whose square is the identity. So that means X square is the identity, Y square is equal to E. What do we need to show? No, we don't need to show. That's what I am saying. We just need to do the first one-step subgroup test. Uh, and we need to show that xy inverse whole square is equal to E, right? That is what it means to be an element of H. By definition, I have defined H as the set of all x in G such that x square is equal to E. So to show that xy inverse is an element of H, we have to show that xy inverse whole square is equal to E. And how do we show that in an abelian group? We have xy inverse whole square is x square y inverse whole square. We saw this in one of the problems. For an abelian group, AB whole square is equal to A square B square. Then This is the same as x square into y inverse whole square, the same as y square inverse. We didn't really show this, I guess, but it is true. No, we directly said it. We said that y power m power n is equal to y power mn. It's also equal to y power n power m. So as long as m and n are integers, you can shift the powers however you want. So y inverse whole square is the same as y square inverse. But we know that x square is equal to e and y square is equal to e. E inverse. E inverse is simply e. So this is e, which is nothing but e. That's why whenever x and y are in H, xy inverse is in H. So by the one-step subgroup test, H is a subgroup of G. Right? Now you don't have to show closure and the existence of inverse separately. And a identity is in the group. None of that you. Okay, identity we showed because we wanted to show H is non-empty. But once you do that, you don't need to separately show that the group is closed and every element in H has an inverse in H. Another example, let G be an abelian group under multiplication with identity E. And H is defined as x squared such that x is in G. So the squares of all the elements of G show that H is a subgroup of G. Yes. If A and B can be written in the form of x square or y square for some elements x and y, then AB inverse can be written in the form of z square for some element z. That's what we need to show. And before that, we have to show that it is non-empty. Only for non-empty subsets, this test holds. So you know that E square is equal to E, right? So E is the square of an element. E belongs to G for all G. So H contains E square, which is the square of E. Therefore, H is non-empty. Now we can come to the test. Suppose X, or let's say A and B, belong to H. That means A is equal to x square, B is equal to y square for some x and y in G. Right? That's what it means for an element to be in H. Then to show that H is a subgroup, we have to show that AB inverse is in H. So to show AB inverse belongs to H. In other words, AB inverse is equal to Z square for some Z in G. For some Z in G, that's how H is defined. It is the square of all elements of G. So if some element belongs with H, then it is the square of some element in G. How will you show this? AB inverse is A is X square, B is Y square. So is X square, Y square inverse. But earlier we saw this can also be written as X square, Y inverse square. Then since the group is abelian, this is also the same as XY inverse whole square. For an abelian group, AB whole square is equal to A square B square. And since X comma Y belong to G, XY inverse belongs to G. So AB inverse is the square of XY inverse. Right? So AB inverse belongs to H. So whenever two elements are squares of some elements of G, then the product of A and the product with B inverse is also a square of some element in G. So that's how you use the one-step subgroup test. This much is clear. Okay, next we'll go to the two-step subgroup test. So this is actually sometimes if you feel one-step subgroup test is a bit difficult to understand, you can use the two-step subgroup test. So for beginners, this is more recommended. So here let G be a group and let H be a non-empty subset of G. If AB is in H, whenever A and B are in H, that is H is closed under the operation of G. And A inverse is in H whenever A is in H. H is closed and are taking inverses. Basically, every element has an inverse within the set. Then H is a subgroup of G. Yes. No, it doesn't say that, doesn't ask you to check if your identity element is in the group. Yes. Both of them combined would lead to that. And it also does says that you don't need to check for associativity. So in the two-step subgroup test, you just had to check if it is non-empty, and once that is uh, done, you just had to do one test. That is AB inverse is in H whenever A and B are in H. Here you have to do two tests. One is the closure test and the other is the inverse. The existence of identity, you don't need to check for it separately, is what it is saying. Yeah. So basically it's saying if all three properties are satisfied, and since if it's a subset of already an existing group, right? So in general, if it's not a subset, if it's just some set, then you need to check all four conditions. But here it's saying if it is a subset of a group and three of the conditions are satisfied, then the fourth is automatically satisfied, is what this is saying. But by three are automatic, I mean the specific property of identities. You don't need to check for an identity if inverses, all those things are. So here the difference is if you just have a random set, right? Then you don't know that an inverse exists for that. If you take an element from a random set, you don't know whether an inverse exists for it or not, right? For example, for integers, 2 does not have an inverse, that you have to check first. 3 does not have an inverse, that you have to check it, and that inverse does not belong to your group. Here, since H is a subset of G, when we say that A inverse is in H, what we mean to say is the inverse of A in G is also an element in H. So the group G gives you a guarantee that in G A has an inverse. And what you need to check is whether that element is in H or not in H. Right? Not that whether inverse itself exists or not. Did you get that point? Yeah. So it is more convenient because it is more like checking whether membership condition is satisfied by the inverse A inverse. But the existence of A inverse is guaranteed in G. So, for example, if you are looking at the general linear group G and its subset, which is the special linear group, then what we're asking is we know that any invertible 2 by 2 matrix that has an inverse, we know that what that inverse is for a 2 by 2 matrix. So the inverse of the matrix ABCD is 1 over AD minus BC into uh, A minus C minus B minus C, be something like that. And what we need to check whether the special linear group, if you didn't know it's a group already, what you would need to check is whether if some matrix has a determinant 1, so it is a member of the set H, set SL, then whether its inverse also has determinant 1. But you don't have to construct the inverse yourself for separately for that a matrix in the special linear group. You can simply take the inverse of that matrix in the general linear group. You only have to test whether that has determinate 1. So that is one use of dealing with subgroups instead of groups. And this proof is simple since H is non-empty, the operation is associative, H is closed, and every element of H has an inverse in H. All that all that remains to show is that E is in H. Then since H is non-empty, let A belong to H, or let X belong to H. Then set A is equal to B is equal to X in the one-step subgroup test. Sorry. Uh, no, we won't do it that way. We'll write set. Okay, let X in H. Then X inverse is in H because inverse. Uh, every element of H has an inverse. Then X into X inverse is in H because H is closed. But X into X inverse is E. So E is in H. So that's it for two-step subgroup test. To check closure and existence of inverse if you know it is non-empty. So this is almost the same as checking if it is a group, right? So it just reduces a little bit, maybe that's all. Maybe not even that, because sometimes to show H is non-empty, we show that the identity is in the subgroup. So then it's almost the same as showing that H is a group. That's why the one-step subgroup test is better. So you would carry out the procedure this way. We'll just do some examples. Let G be an abelian group. From these examples, more than the test and applying the test, that's just routine stuff. The subgroup themselves are nice. So this type of thing It's not uh, clear at first glance that the set of all elements whose square is the identity will be a subgroup, or the set of all squares of elements of a group form a subgroup. So these examples are nice in that sense. But applying the test to the problem is simple once you have the problem proper. If once you understand the problem proper. Then H is set of all x in G such that, or the order of x is finite. This is a subgroup of G. How do you solve this? Using the two-step subgroup test. Yes, order of. We are saying all the elements with finite order in an abelian group. The fact that it is abelian is important in all the examples that we have done till now. Yes, yes. They're yeah. That's why they let these kind of nice subgroups exist. Now, first we have to show it is non-empty always. What if there is no element such that? What if the group? Yeah. So now we can come to the two-step subgroup test. We have to show two things: closure and existence of inverse. So let A comma B belong to H. And how do I show that AB is in H? So let's write down some numbers. Let's say let order of A be M and order of B be N for some Mn in some natural number Mn. Yeah, we have to show AB has finite order. Okay. So if K is a multiple of M, then that is true that A power K is E. If it's not a multiple of M, then it need not be right. A power M is E, but A power M plus 1 is A. It is not E. So you have to give one number K, that K you have to pick such that A power K is E and B power K is also E. Some number that makes it both A power K and B power K go to E. What would be that number? You have to give one number. Maybe that is not the order. Maybe there's just a smaller number that is the order. But if you give one number, the order will always have to be less than or equal to that number. So it will be finite. So what is that number? Yes, we can try Mn. AB power Mn. Since it's abelian, we can write it as A power Mn, B power Mn. Then, like I showed here, um, with this notation, exponential laws hold. So A power Mn can be written as A power M power n, and B power Mn can be written as B power n power m. Yeah, so this is, yeah, so this is E power n E power m, and that is nothing but E times E. This is equal to E. So we have given one positive integer Mn such that AB power Mn is E. But the order of AB might actually be, it doesn't mean that it is Mn. It might be some number that is smaller than Mn. But what we needed to show was that the order is finite, not that the order is Mn. So if it's Mn or less than Mn, it's still finite. So order of AB, let's say, is finite. Thus, A B belongs to H implies AB is in H. That is one step of the two-step subgroup test. The other step is we have to show that A inverse is also in H. Yeah. So A inverse has a finite order. Thus, A is in H implies A inverse is in H. So by the two-step subgroup test, as H is a subgroup of G. Next, we'll do another example. This is a more important example because it gives you a method of constructing subgroups in general, and it will be used later lectures also. It might be used. So let G be an abelian group, and H and K be subgroups of G. Then HK is defined as set of all H times K, where H is an element of capital H and K is an element of capital K. Show that HK is a subgroup of G. So you already have two subgroups H and K. For any element of H, you pick any element of H, then you pick any element of K, and you take their product HK and you put it in the set capital H capital K. which is the set of all products of element, first element coming from H and second element coming from capital K, where both capital H and capital K are subgroups. So how would you solve this? Yes, this is using the binary operation. First we have to show it is non-empty. So since H and K are subgroups, H and K are subgroups of G. Yeah. So E belongs to H, E also belongs to K. So E dot E which can be written as E dot E belongs to HK. Thus HK is non-empty. Ah, it is abelian. That's why we took it abelian. Otherwise it won't be subgroup. Yeah. So this belongs to H because H is a subgroup and H1, H2 are elements of H. So H is closed under the operation. That's why we wanted H to be a subgroup. Also, since K is a subgroup and K1, K2 belong to capital K, K1 times K2 belongs to K. So now AB is a product of an element of H and an element of K. So AB belongs to HK. So we showed that if A and B are in HK, AB is in HK. Next, we have to show that A inverse is in HK. So A inverse is then what? Yeah, so this is K1 inverse, H1 inverse. Then abelian property you can use to write it as H1 inverse, K1 inverse. Since H is a subgroup, H1 inverse is also in H. And since capital K is a subgroup and K1 is in H, so the K1 is in capital K, K1 inverse is also an element of K. So A inverse can also be written as an element of H times an element of K. So this implies A inverse belongs to HK. So by the two-step subgroup test, HK is a subgroup of G if G is abelian. So this is one way to, this is also some type of product, I don't remember the name. But there are methods to form products. That's one called external direct product. So like that, there are products of groups or product of subgroups. You will see that in later classes. Finally, we'll go with a non-example. That is, if every subset of a group was also a group, then there would be no point in talking about subgroups. So that the fact that we are talking about subgroups means that there are subsets of a group which are not groups themselves. So one such example would be this. If we consider G as the group of all non-zero real numbers, that is R star, and H is the set of, it is it contains one or X is irrational. That's one subset. K is the set of all X in G such that X is greater than or equal to 1. That is another subset. Then H is not a subgroup of G. Why is that? Inverse would also be irrational. There's no problem with that, right? Inverse of root 2 is 1 by root 2. 1 by root 2 is also irrational. And 1 is also has an inverse, which is 1 itself. So inverse is not a problem. Yeah. Flow identity is also there. Associativity is also there. So if I'm saying it's not a subgroup, then closure must be the problem. And how would closure be the problem? Yes. Which two irrationals? You can't randomly take any two irrationals because, okay, I will take square root of 2 and square root of 3. Square root of 2 into square root of 3 is square root of 6, which is irrational. So that doesn't violate closure. Yeah. So if you take square root of 2, which is an element of h, but square root of 2 times square root of 2 is equal to 2 is not an element of h. So h is not a subgroup. Then if we take k is also not a subgroup. And what is the reason for this? Closure. What about closure? If two numbers are greater than or equal to 1, is their product also greater than or equal to 1? Yeah, so closure holds. And 1 is greater than or equal to 1. 1 is equal to 1. So identity is also there. Associativity follows from the associativity of multiplication for non-zero real numbers. So only thing left is to check for inverses. What would be the inverse of an element of K? If you pick a number greater than or equal to 1, what is its inverse? Yeah, but does a fraction belong to K? The condition is x is greater than or equal to 1. Can a fraction be? Yeah. So if I take a natural number in K, then the fraction you get is 1 over that natural number, which will always be less than or equal to. In any case, even if it's not a natural number, if you take some number that is greater than 1, some positive number, and you take the inverse of that, that would be less than 1. So 2 belongs to K, but 2 inverse does not belong to K. Or if you take 3 by 2, which is 1.5, which is greater or equal to 1, its inverse is 2 by 3, which is 0.67 or 0.666, which is less than 1. So in this case, the inverse does not exist. The inverse exists in the larger group, that is the set of non-zero real numbers, but the inverse does not exist within H itself. So H is not a subgroup and K is not a subgroup. Okay, we'll stop here, and next class we'll continue next week with uh, a subgroup test for a finite set. That's a bit more simpler, like how we discussed earlier. For a finite set, that inverse will always be there as long as closure is satisfied. So in this two step, we had to check for the existence of inverse and closure. But for finite group, if you check for closure, that is enough. Inverse will always exist if closure uh, holds. Then we'll see some examples, and we'll see some. Uh, we'll see what is a cyclic group and cyclic subgroup. After that, we'll do problems. Okay. Bye.